This
Yes.
conference will now be recorded.
So, very good evening, students. We have been discussing kinetic theory of gases. So today we'll be learning very important topic, and based on this, there will be many numerical problems in competitive exam. So today's class is really very important. So what are we going to discuss today? We are going to discuss the actual kinetic theory of ideal gas. It includes the assumptions made by Clausius and Maxwell to develop the kinetic theory of gas. Those assumptions are really very important. Then we'll establish the expression for pressure exerted by a gas, and we'll try to find out some corollaries from that particular expressions, like interpretation of temperature, then the relation between pressure and kinetic energy, etc. So the derivation part is important here, and the expression we will be getting, we will be using to calculate various other parameters as well from here. Okay, so as we all know, all materials or matter eh, are made of molecules, right? In case of solid or liquid, molecules are very tightly bound. They are very close to each other, so they have strong molecular intermolecular forces. But in the beginning itself, we have seen the molecules of gas. In this chapter we will be discussing that the gases of the molecules of the gas are in a random motion, are in a random motion, continuous and random motion, and their velocity depends on temperature. As you know, temperature is directly related to internal energy or vice versa. So to develop the kinetic theory of gas, especially for ideal gas, there were some assumptions made. We'll learn the assumptions one by one. You should, by heart, you should know these assumptions. When we talk about kinetic theory of gases, you should be remembering those assumptions. So the first assumption is that all gases consist of molecules, a large number of molecules. But what is the nature of the molecule? Molecules are rigid, elastic sphere, and identical in all respect for a given, for a particular gas, for a given gas. Like suppose I say oxygen. So oxygen has, suppose, some Avogadro number of molecules. So all the molecules are identical sphere, and elastic, perfectly elastic, rigid, and all the molecules are identical for a given gas. But if I take oxygen and nitrogen, then the molecules are rigid, elastic, everything is fine, but they are not identical. These are not identical. Okay, so this is what is stated in this assumption. So elastic identical spheres are identical in all respect for a gas and different for different gases. Now the size of molecule is negligible compared to the average distance between the molecules. So as I was saying you that, or you might be knowing, in case of gas, the gas molecules are far apart from each other. When the gas molecules are far apart from each other, then they may not have much interactions or negligible interactions. For ideal gas, there is no interactions. So here, this second assumption is saying that size of molecule is is very small compared to the average distance between the molecules. So this, suppose this is the distance. So the radius of this molecules will be much much lesser than the distance between two molecules. Okay, this suppose one, this is two. So their size may be very tiny. So this is O2, this is O1, and this is the path. Okay, or the distance between two molecules. So the size of the molecule will be much lesser than the interatomic distance between intermolecular distance, average distance between the molecules. The molecules are in a state of continuous random motion. As I was saying you, molecules are not at rest or stationary. They are randomly moving, and that motion is also continuous, and it is moving like gas molecules will move in all directions. If I talk about three dimension x, y, z Cartesian coordinate system, if I consider, okay, so the molecules are in a state of continuous random motion, moving in all directions. So a gas molecule can have a freedom to move in this side, to move in this side, again to move in this side. So it is completely free to move in any direction. So gas molecules can move in any direction, any of the three directions. Sorry, not any, all in all three directions. Now, as I said, that the gas molecules, they will be actually randomly moving. But see, a particular gas is actually made up of a large number of molecules. A large number. What is the number? If we take minimum Avogadro number of molecules, so that is 10 to the power 23. So a huge number of molecules, when they are randomly moving, randomly moving, then what happens? Then there will be collision. There will be collision between, see, this collision will be happen with other molecules, okay, and also with the wall of the vessel, okay. So during random motion, the molecules collide with each other and with the walls of the vessels. Actually, this is the origin of pressure, okay. This is the origin of pressure. When the gas molecules are confined in a particular vessel, then they continuously and randomly moving, and during their motion they collide with each other. At the same time, they collide with the walls of the gas also. Therefore, there will be a pressure exerted by the gas on the vessels. Now, collisions, what are the, see, there are two types of collision at least broadly, we know. One is elastic, another one is inelastic. So in this case, the collisions are perfectly elastic and there are no forces of attraction or repulsion between the molecules. Thus, all internal energy of the gas is kinetic energy. So what we are talking, the fifth assumption, you look the fifth assumption, the collisions are perfectly elastic. That means there will be no loss at all, no loss of energy. Perfectly elastic, there is there are no forces of attraction, repulsion between molecules. If there is no attraction and repulsion between molecules, then will there be any potential energy? No. If there are no attraction, repulsion, etc., then there is no potential energy. Only energy available will be the kinetic energy within the gas. Then we have few more assumptions. See, when these gas molecules are moving, see they are moving very randomly, like this. Any way they are moving. So suppose there is one molecule over here, another molecule here, here, here. These are, suppose these are all molecules. Okay, so between two successive collisions, actually they are moving in a straight line. See, these are two collisions. Suppose these are two collisions. First collision, second collision happens, and this line of joining the molecules actually called mean free path. Okay, so between two collisions, a molecule moves in a straight path with uniform velocity, a particular velocity, constant velocity, straight line at the same time constant velocity. The average distance covered by molecules between two successive collisions is called the mean free path. As I said, the velocity between two successive collisions will be a constant velocity, that is this one, and the distance they travel between two successive collisions is called mean free path. Then the collisions are almost instantaneous. That means the time during which a collision lasts in a negligible compared to the path of mean free path between two molecules. The collisions are almost instantaneous. And the last one is that despite the molecular collisions, the density of the gas remains uniform throughout the gas. Despite the molecular collisions, density remains the same throughout, or that will be uniform throughout the gases. Okay, so these were assumptions. Now we'll derive an expression for the pressure. Pressure that an ideal gas exerts on a vessels. So before we derive the expression for the pressure exerted by gas, let me tell you the fact once again how gas exerts pressure on the vessels. So as you have seen in the assumptions that a gas is constituted by a large number of molecules, and those are moving randomly, and they have no attraction, no repulsion. So all the energy is kinetic energy, and with that kinetic energy they move, and while they move they collide with each other. Okay, collide with each other and with the wall of the container. And since the collision is elastic in nature, after the collision with the wall or maybe with another molecule, there will be a change in the path of the molecule. Hence, there will be change in the magnitude and direction of the velocity vector. Okay, or we can say after the collision with the wall, since the collision is elastic, collision, so there will be no loss of energy, no loss of kinetic energy. Okay, but there will be change in the momentum. Okay, the change in the linear momentum we can find out, and if we know the change in the linear momentum, so linear momentum p, change in the linear momentum due to the change in the velocity, then this is momentum, then we can find out the force. Dp dt is equal to force. Then once we get the force, then we can divide that with area of cross section of the container. So that would give you the pressure expression for the pressure. Okay, this is how you should do. You should first be able to find out the expression for the force, and then you know the vessel like area of the vessel is A. So then you can write thrust by area is equal to temperature. So sorry, this is this pressure. I'm sorry. So thrust by area will be the pressure. Okay, this is how we have to actually derive the expression. So this is brief discussion on how we will be discussing. Deriving the expression for the pressure exerted by gas. Now we'll just go to the fact. So let us consider an ideal gas which is enclosed. Let us consider an ideal gas which is enclosed within this cubical vessel. Okay, within this cubical vessel, And let us suppose the area of the wall, all the walls is A, and let us suppose the walls are parallel to the coordinate axis in Cartesian geometry or Cartesian coordinate axis system, Cartesian system. So like see this X is supporting this particular wall. So we have taken the cubical vessels whose walls are parallel to the coordinate axis. Now let n be the number of gas molecules per unit volume. Number of gas molecules per unit volume. Okay, this is the number density of the molecules, and let each of the molecules and each molecule has a mass small m. Okay, now let us take only one molecule as a representative one, just to establish the expression. Let us just consider a single gas molecule. As you see, it has velocity in all direction. As we know, it can move in all direction. So it has velocity components along the x direction this way, along the y direction this way, along z direction. It can move in any direction. So there are three different velocity components for a particular molecule. And suppose the molecule just move from here. Okay, move from here, maybe the middle portion, and just hit the wall. You can see that this wall, which is parallel to yz plane, it hits this wall, and after hitting the wall, it rebounds. Since the collision is elastic in nature, so it will rebound. Okay, after hitting the wall, it will rebound. And see, when it is moving, from this place, like this place, and hitting this particular wall, which is this particular wall, it has to return back. So it will hit this wall and return back, because the velocity, because the collision is elastic in nature. And one more thing is that we here, particularly we are considering this direction, right? This direction, this is actually x direction, and this is minus x direction. So the velocity also, since velocity a vector, it will also have different component. So when it rebounds, it is moving in the opposite direction of x-axis. So that's why velocity component only changes. Velocity component along the x-axis, it changes. Okay, changes by at least here it changes with the direction. Okay, So what I'm trying to say is that, see, suppose there is a molecule here. It has velocity components x, vx, vy, and vz. But now we are just looking at this molecule. See, it comes here and hit the wall and just go back or rebounds to the rebounds to this direction. Okay. So when it comes here, so it has both components. It has both components, like this is vy, suppose this is vx. Similarly here, this is vx, this is vy component of the velocity. Okay, so now you look this, there will be change in the velocity, there will be change in the velocity along x-axis only. Otherwise other things are all right. So this is along this direction, that is fine. So here also the velocity component along y-axis is constant. Only change is there in the x direction. So change in the velocity will be minus of minus 2 vx. So this will be the change in the velocity. If I say what is the change in the momentum in this case, then you write mvx minus of minus mvx. So this would give you change in the velocity, change in the change in momentum. Change in momentum will be 2m into vx. Okay. If you don't understand, let me tell you once again. See here, gas molecules initially comes in this direction, and if I break the component of the velocity, suppose velocity vector, I have both x component and y component. So when it moves parallel to x-axis, or it is hitting this particular wall and then rebounds, then the velocity, other two velocity component does not change, only the x component change. Okay, so that's why there will be a change in the linear momentum, that is 2 mvx. Linear momentum changes to vx. Okay, so we have got change in momentum for a particular gas, for a particular gas. Okay, so let me go to the next page and then let me tell you, this is expression for, still we are there, expression for pressure. Pressure exerted by a gas or an ideal gas. Anyway, things will be almost same at low pressure and high temperature. Okay, so suppose in a small time interval, in a small time interval dt, in a small time interval dt, sorry, delta t, all the molecules which all the molecules which lies within the volume A into Vx. So those only are actually making a change in the those molecules for which there is a change in the momentum, linear momentum, is that this. So volume is A into Vx. Now see the molecules which lie in the volume. Okay, there will be delta T also. So the molecules which lie within this volume only will hit the wall. That is what it is said. So see molecules are here with this velocity component. So the molecules will go and hit. Those molecules only will go and hit which are there within this region. Okay, so A Vx dt delta T. Okay, so within this volume, the molecules in the container will be certainly going and hitting the wall of the container. Okay, so within this volume, the number of molecules within this volume. Now we had an expression for change in the linear momentum for a single gas. So single gas molecule. But now if we go for n number of molecules, the figure will change. Okay, that will be a huge figure. So lie within the will hit the wall. Okay, so now we are calculating the number of molecules within that wall, that volume. Number of molecules within that volume. So we have A Vx delta T and parent volume, there is small n number of molecules. So within this volume there will be A Vx delta T into n number of molecules. Once again, see all the molecules at a time may not go and hit the wall. So some of the molecules are going forward and some of them are like half of the molecules are going forward and half of them are coming back. So we can find out the average number. Okay, average number of molecules. Actually, number of molecules within the volume A Vx delta T which hits the wall is half of this number because half molecules are going and hitting the wall and half of the molecules are coming in the opposite direction. Okay, so anyway, so the molecules towards the wall and the other halfway from the wall. So actually we have considered, if you remember, we have considered the molecules from this halfway to this wall. That's why we said Vx A delta x or del x. Okay, so half of the molecules are hitting. So half into A into Vx into delta T into N. These are the molecules which are hitting the wall. Now we can find out total amount of momentum transfer or momentum change. See, when a ball hit like this and the ball rebounds, so it is said that the pressure uh, when the gas molecules just hits and comes back, there will be change in the momentum that we have seen, and we have got the average number of molecules within the volume A Vx delta T into N divided by 2. This is the average number of molecules which are taking part in the collision. So for this number of molecules only there will be change in the linear momentum. What is the change in the linear momentum? Change in the linear momentum. So change in the linear momentum or transfer in the linear momentum will be delta P into 2m Vx. This is the momentum change for only one, and these are the numbers. Okay, so if we simplify this, what we get, 2 goes off. That's all. So, but if we want to calculate the force exerted, then the force will be the rate of change of this linear momentum. Okay, so this would give you mvx a into x dt. Okay, and there is a number here n, here also n. So this is the, I'm sorry, there will be no dt. Let me write mn. mn mn, then you have 2v x, so vx square into a into n here, this factor, this would give you force. Then what is the pressure? Pressure means force exerted by exerted force or thrust divided by area. So mn, so this is actually, I'm sorry, there are two n, no, this n will not be there. V, okay, a has come, all right. So mn into v square, vx square Okay, now see there are actually many molecules. Even in the x direction also, when molecules are moving, they may not have the same velocity vx. They may have uh, ranges of velocity. Vx will be ranging from suppose 0 to some value, and then that value to some other value, etc. So all the molecules will not move in the same with the same velocity. So that's why we can take the average velocity, and hence we are writing the expression here that the pressure is mn into vx squared, and this v you have to take average v because all the molecules are not moving with the same velocity. Okay, so thus we get the sorry expression for pressure in a particular direction along x direction. So what is that? M into n v x squared, that is average v average x squared. Now if we had considered only the motion of a gas along the x direction, if we consider for other direction vx, then average vy, then average vz. Okay, vz. Now we can do one thing, we can write this as 1/3 of vx plus vy plus vz. Okay, now this is, since it is square, we can just make this square, and there will be, so this is, I'm sorry, this, yes, so we can write 1/3 v average square. So we can express this vx in terms of all other component. So that's, so here m into n, and vx is x square, we can write v 1/3 v average square. So that's how we get 1/3 mn, 1/3 mn v average square. This is the pressure exerted by an ideal gas. Okay, so actually this happens only for isotropic medium. Now see what we know, that this is the number of molecules per unit volume, this is the mass. So if we take 1 into n, that means mass is 1 kg. Okay, mass is 1 kg. Then this would give you actually the number density. Sorry, this is actually, yes, this is another density, mass density. This is, so mass density means mass by volume that we know. So here when we talk about 1 gram of, sorry, 1, okay, let me tell you this, this can be written as rho. So I have suppose one. See, I have density means total mass of the substance divided by mass divided by volume. So mass suppose m into n divided by volume. Actually per unit volume. So this is actually mass per unit volume is rho. So if it is per unit volume, then mn can be considered as one third rho v average square. Okay. So mn actually gives you m into n gives you the number density. Okay, so finally what we have got? Finally we have got the expression for the pressure P is equal to one third rho v square. V obviously v average square, v in all direction. Okay, so this is the expression. You if you just patiently sit and read this, you'll get the concept. And now we'll just discuss a simple concept. Uh, Kinetic energy and pressure, they have a particular relationship. Okay, so pressure exerted by a gas and average kinetic energy per unit volume, they have a particular relationship. We'll go to the next page. So relation between relation between the pressure and kinetic energy per unit volume. Per unit volume. Okay, so what we know? We know this already. Rho v average square. Now mass per unit, mass per unit volume. What it is? Mass per unit volume. That would be rho. Okay. Now, if we take average velocity, sorry, average kinetic energy, then average kinetic energy is actually translational kinetic energy per unit volume of gas is given by half rho and v average square almost. So this is actually the average kinetic energy, average kinetic energy, average kinetic energy of translation per unit volume, translation per unit volume, per unit volume of the gas, this one, this is the average kinetic energy, but that is per unit volume. So we have got two expressions. One is pressure, another one is for gas. Sorry, kinetic energy. Then we can write, you look what we can write. We can write pressure divided by kinetic energy. Pressure is one third rho v average square. divided by half rho V average square. So everything goes off. You can see what we will get is 2 by 3. Okay, 2 by 3 means the pressure will be two-thirds of the average kinetic energy per unit volume. So this is a special relationship between kinetic energy, average kinetic energy of average kinetic energy of gas molecules and the pressure. The pressure exerted by a gas is equal to the two-thirds of the average kinetic energy of translation per unit volume of the gas. Okay, so this is, I'll just write it and then stop the class. So this is the pressure exerted by gas, exerted by the gas pressure exerted by the gas. See what are the assumptions here? Pressure per unit volume, right? So exerted by the gas will be two-thirds of the average kinetic energy. Average kinetic energy of translation per unit volume. Okay, so we'll stop it here. We'll take this pressure as our reference, or using this expression P is equal to one-third rho v square. We'll be trying to give the interpretation of kinetic energy, sorry, interpretation of the temperature. So kinetic interpretation of temperature we'll see. We'll see most probable velocity. We'll see there is a distribution of velocities for the molecules, gas molecules. They won't always move with the same velocity, but they have distribution of velocities. We'll see that when we discuss most probable velocity of gas molecules. So that we'll learn tomorrow. Okay. So I'll stop it here for today. Thank you for your patience.